Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. During last 5 clips, we have discussed different kinds of compactness, their one-on-one relation, and we have seen some of them are equivalent in first countable T1 spaces. We have studied metrizable spaces to some extent, then Lebesgue numbers, epsilon net, total boundedness of metric spaces also studied, and lastly we have characterized sequential compactness of metric spaces. Today we'll prove that in case of metrizable spaces, all the 4 kinds of compactness that we have studied, the compactness in classical sense, countable compactness, limit point compactness, sequential compactness, all are equivalent. So today we are going to prove the result that says in case of metrizable spaces, compactness countable compactness, limit point compactness, and sequential compactness are all equivalent. That is, one implies the others. Okay, so let's prove this result, but let me sketch the proof. Okay, let X be a metrizable space. Since metrizable, so there exists a metric D on X that induces all the open sets in X. So let D be a metric on X that induces all the open sets in X. Okay, so we may assume that we are in a metric space XT. We know in case of metric space, countable compactness, limit point compactness, and sequential compactness are equivalent. So in XT, countable compactness, limit point compactness, and sequential compactness are equivalent. We have done it, is done already. Okay, and we also know that compactness implies limit point compactness. Okay, so now if we prove that this sequential compactness also implies compactness, then we will get this diagram. Look at this. So compactness, limit point compactness, sequential compactness, and countable compactness. Okay, so if we show sequential compactness implies compactness, then what happens? Let me show. So from this, compactness implies limit point compactness. Fine. And limit point compactness implies sequential compactness. Fine. Sequential compactness implies limit point compactness. Limit point compactness implies countable compactness. So sequential compactness implies countable compactness. Sequential compactness implies countable compactness. Okay. Now countable compactness implies limit point compactness. Limit point compactness implies sequential compactness. If we show this, then the sequential compactness will imply compactness. So ultimately countable compactness will imply compactness. Okay, so this cycle will be completed. If one of them is true, say this, then any one of the other three will be true, isn't it? So this equivalence will be proved. So just in order to show, in case of metriable spaces, these four kinds of compactness are equivalent, just it remains to show that sequential compactness implies compactness. Clear? So let me prove this. Fine. Here we will use many properties of sequential compactness. We know if a metric space is sequential compact, then every open cover has a Lebesgue number. We know sequential compact space is totally bounded. We will use all those things. Okay, so it is sufficient to show that sequential compactness implies compactness. Okay, we'll assume that the metric space XD, this metriable space, so metric space is sequential compact, and we will prove that it is compact. Fine. Okay, so in order to show the metric space XD is compact, assuming that it is sequential compact, we have to start with any open cover of this, and somehow we have to find finite number of members from this open cover that also cover the space, whole space. Okay, so let script C be any open cover, of this space XD. Okay, since this metric space XD is sequentially compact, so every open cover has a Lebesgue number, so this open cover has a Lebesgue number. So script C has a Lebesgue number. Okay, script C has a Lebesgue number, say delta, of course greater than 0 by definition. Okay, again, since XD, this metric space, is sequentially compact, it is totally bounded. Totally bounded. Okay, fine. Totally bounded, you can recall. So whenever we take an epsilon greater than 0, we will get finitely many open balls, each of radius epsilon, that can cover whole space XD. So in particular, so it is totally bounded. Since this is sequentially compact, it is totally bounded, and hence it has an epsilon net for every epsilon. So for epsilon equal to delta by 3. Okay, and let it be this x1 x2 dot xk. Epsilon net is a finite subset of the space, so that the open balls centered at those points of the finite subset, each of radius epsilon, can cover whole space, So here epsilon is delta by 3, and let that epsilon net is this. That is, if we consider open balls centered at those points, each of radius delta by 3, then it will cover whole metric space HD. Okay, then what will happen? Then this union BD x1 delta by 3 union BD x2 delta by 3 union BD xk delta by 3. This union will be whole x. Fine. Now since every such open ball, every such open ball has diameter, radius is delta by 3, so diameter 2 delta by 3, that is less than delta. So every open ball has diameter less than delta, and delta is a Lebesgue number for this open cover. The delta is Lebesgue number for this open cover means whenever we take a subset of X having diameter less than delta, it will be contained within a member of script C, isn't it? Since every such open ball has diameter less than delta, so for every such open ball we will get a member in script C containing that open ball. Okay, so there exists, say, OI in script C such that this BD xi delta by 3 totally contained in Y for I equal to 1 to k. Okay, fine. Now since these open balls, this k many open balls cover whole X, and OI are bigger than these open balls, so this O1, O2, O3 up to OK, this being bigger than these open balls, so they will also cover X. Okay, so this O1 union O2 union dot OK will cover whole X. Okay, and they are members of script C. Script C, any open cover of the metric space. So script C, any open cover of the metric space HD, and we found k many members from script C, O1, O2, O3, O4, OK, so that their union is whole X. Okay, so X is X or XD, same, XD is compact. Okay, so we have proved that sequential compactness implies compactness, and as I said, sequential compactness implies compactness. It means all those four kinds of compactness are equivalent. So in case of metriable spaces, all those four kinds of compactness are equivalent. Fine. Now just a minute. What happens? Okay. Now you know closed and bounded subset of a metric space may fail to be compact. You know, so as a note, that a closed and bounded subset of a metric space may fail to be compact. Okay. In general, in a metric space, if a subset is closed and bounded, then it may fail to be compact. For example, let x be infinite set and D be the discrete metric dxy equal to 0 when x equal to y and 1 when x not equal to y. Then you know the singletons are open balls. In the last clip we have discussed most probably. Okay, bdxr, it will be singleton if 0 less than r less or equal to 1, and it will be whole x if r greater than 1. We have discussed. Okay, fine. So let A be an infinite subset of x. Okay, infinite subset of x. Fine. Since A subset of x and x is, look at this, if we consider r greater than 1, so it will be whole x. So x is bd for any x, consider 2. So A can be placed within an open ball, so A is bounded. Since A containing this, A is bounded. Okay. Okay, and this A is closed also. A is closed. Why? Look at this open ball. Every singleton set is an open ball. If we consider R just less or equal to 1 greater than 0. Okay. Since every singleton is open, so x minus a, it can be written as, say union of b in x minus a. Okay, just we are taking element from this and we are collecting again, so we will get ultimately this, that is this. Okay, since every singleton is open, so this x minus a is open, this is open, and hence x minus a is open, hence a is closed. Fine, A is closed. So A is closed as well as bounded. Now I will show it is not compact, and it is very easy. but A is not compact. A is not compact. What is the reason? Because the script C equal to the family of all singleton subsets of A, where A in capital A. Okay, every singleton open. Okay, so this is a family of open sets. Okay, and if obviously if we take union of this family, all elements of capital A will be members of that union, isn't it? So A will be covered by this, because this is an open cover having no finite sub collection that can cover A too. Okay, no, that can cover A. Okay, so because since A is infinite, so there are infinitely many members. Okay, if we take just finitely many from this, only that finite subset of A will be covered. Okay, all other members will remain uncovered. So one cannot get finite number of members from this. Okay, so that can cover A again. Okay, fine. So A is not compact, though it is closed and bounded. Okay, so a closed and bounded subset of a metric space may fail to be compact. Okay, I can give you one more example. Okay, you can check. This is also an example for showing the same. Okay, so one more example. One more example is L2. L2, you know. Okay, L2 is the collection of all sequences. All sequences, say x equal to xn, of complex numbers such that this infinite series mod of xn square is convergent. That is, this sum is finite. Okay, that is strictly less than infinity. This L2, which is the collection of all sequences of complex numbers satisfying this condition, with the metric this dxy, this equal to summation n equal to 1 to infinity mod of xn minus yn whole square. Okay, for all x equal to xn, y equal to yn in L2. Okay, so consider this metric space L2, where the underlying set is the collection of all sequences of complex numbers satisfying this property, and the metric is defined in this way. Okay, now if we take the A, which is the collection of all such members like this, EM, this is nothing but del M conical delta n varies. Okay, n equal to 1 to infinity m in n. So if we consider E1, E2, E3, E4, so on, This A is the collection of all those E1, E2, E3, dot 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 dot. And E1 means this del 1n. So if n1, then del 1 1, that is 1, and for other n 0. That is E1 is 1 0 0 0 0 0 endless. E2 is 0 1 0 0 0 0 endless, in this way. So this A is the collection of all those EM, where M in this. This is closed and bounded but not compact. This is closed and bounded. Bounded, of course, closed and bounded, but not compact. You can check. Okay, as simple as that. Fine. So now, what is this? Oh, it did not work. So another page I should take. So we have seen that a closed and bounded subset may not be compact. But interestingly, okay, so we have seen that a closed and bounded subset, of a metric space may not be compact. Okay, but interestingly, every compact subset of a metric space is closed and bounded. Every compact subset of a metric space is closed as well as bounded. Closed and bounded. Okay, so for every compact subset of a metric space is closed and bounded. First of all, let me prove the closedness. Okay, for we know that we have proved that in some class we have proved that every compact subset of a T2 space, compact subset of a Hausdorff space is closed. We have proved, no? So we know that compact subset of a T2 space is closed, and we know metric spaces are T4 hence T2. So compact subset of a metric space will be closed because metric space is also T2. Okay, so compact subset of a metric space is closed. Fine. Now boundedness. Okay, boundedness. Now let C be a compact subset. C be a compact subset of a metric space xt. Okay, and small a is a point of any point of this C. Okay, now consider the open cover compact, so every open cover will have finite subcover, isn't it? Consider the open cover script C consisting of this open ball BD centered at this particular point A, radius n varies within the set of natural numbers. Okay, so if this is the metric space XD, and if this is the compact subset C, we have considered any point A within C. Now this script C is the collection of all open balls. Okay, each centered at the point A, having radius 1, 2, 3, 4. So we'll in this way, in this way, in this way, in this way, in this way. So ultimately C will be covered, isn't it? So they consider the open cover this of C. Okay, since C is compact, there will be finitely many members this, okay, covering C. So there exist say BD A N1, BDA N2 dot dot dot, BDA N K, such that their union will cover C, such that this union BD A N I equal to 1 to K, this cover C. Okay, now let small m, this be the maximum of this n1 n2 dot dot n k. Okay, then what will be this union? Obvious, if this is A, say this is A, this is n1, say this is n5, say this is n3. Okay, in this way. Now if we take the maximum of all those n, then that maximum radius, if we take as radius and that A as center, then that open ball will be the union of all those open ball. Here this open ball is the union of all these three open balls, the bigger one. So then this union will be actually BDA, this maximum, and it contains C. Okay, so C is placed within an open wall, hence C is bounded. Okay, and this implies C is bounded. Okay, so compact subset of a metric space is closed and bounded. Closeness is shown here and boundedness is shown here. So what we are getting? We are getting that closed and bounded subset of a metric space may not be compact, but a compact subset of a metric space is closed and bounded. So Einstein theorem is partially true in general. Einstein theorem is true only for R or Rn, C, actually in finite dimensional space, in finite dimensional non-linear space, Okay, this Hein-Boyle theorem is true. In case of metric space, Hein-Boyle theorem is partially true, and more concretely we can say so. As a note, we can write that statement of Hein-Boyle theorem regarding compactness is necessarily true. Is necessarily true, but not sufficient in general. Okay, necessarily true. Why? Because if the subset is compact, then it is closed and bounded. Not sufficient because closed and boundedness are not sufficient to declare that subset is compact. Okay, so by using Hein-Boyle theorem, we cannot characterize compactness of metric space. No, but it does not mean that there is no characterization for compactness of metric spaces. Actually, we have already constructed many characterization for compactness of metric spaces. Okay, so follow me. That just few minutes back we have proved that in case of metric spaces or metrizable spaces, this compactness, sequential compactness, limit point compactness, and countable compactness are all equivalent. Okay, and we already proved in the most probably in the fifth clip that a metric space is sequentially compact if and only if it is complete and totally bounded. And a metric space is compact if and only if it is sequentially compact. So we can say a metric space is compact if and only if it is complete and totally bounded. So it will give you a characterization of compactness of a metric space. So the result we are getting here that a metric space is compact. A metric space is compact if and only if it is complete and totally bounded. Isn't it? So this characterizes compactness of metric space. Another, compactness and limit point compactness are also equivalent. Okay, so we can say a metric space is compact if and only if it is limit point compact. And limit point compact, what is the definition? Definition is if every infinite subset has a limit point. So a metric space is compact if and only if it is limit point compact, if and only if every infinite subset of it has a limit point. Okay, so a metric space is compact if and only if every infinite subset of it has a limit point. So this is also a characterization of compactness, characterization for compactness of a metric space. Again, we know compactness and sequential compactness. Okay, done. Compactness and countable compactness are equivalent, isn't it? Fine. So the result is a metric space is compact if and only if it is countable compactness, and countable compactness means every countable open cover has a finite subcover. Okay, it is not necessary to take arbitrary open cover. So a metric space is compact if and only if every countable open cover has a finite subcover. So to check compactness of a metric space or metrical space, just we have to take arbitrary countable open cover. Okay, we may just we have to take countable open cover. Okay, we need not to take arbitrary open cover. Okay, fine. This, so another result that I have written here, just using the characterization of sequential compactness, I should mention here that result: a metric space is compact if and only if it is sequentially compact. Sequentially compact means if every sequence has a convergent subsequence, isn't it? So a metric space is compact if and only if every sequence therein has a convergent subsequence. Okay, and this last characterization of compactness of a metric space actually will be used in function analysis. In function analysis, we often use this characterization. Okay, so this is all about the variety of compactness and their equivalence in metric spaces. Okay, and in the next clip we'll consider another kind of compactness, okay, which is called local compactness. So thank you and keep watching.